Hello, everyone, and welcome back. Today, we are diving into radiation dosimeters, essential tools used in clinic and radiation protection to measure radiation dose accurately and precisely. We will explore how these devices work, their applications in clinical and protective environments, and some essential properties that determine their accuracy and reliability. We will also discuss uncertainties, including the different types and how they impact measurement results. Radiation dosimeters are devices that measure ionizing radiation exposure, air karma, and/or absorbed dose, essential metrics for monitoring radiation. They are used to track radiation levels in clinical settings to ensure safe dose administration and in radiation protection to safeguard individuals. In addition to this, dosimeters are also commonly used to monitor ambient dose equivalent or personal dose equivalent, which reflect the radiation impact in a given environment or on an individual, respectively. In clinical applications, energy deposition is typically measured in gray, while in radiation protection, measurements are often recorded in sievert to account for biological effects. In medical clinics, dosimeters play a crucial role in tracking patient doses during diagnostic procedures like X rays, CT scans, and radiation therapy. Some common types include ionization chambers, such as the Farmer type chamber for general dose measurements, parallel, parallel plate chambers for surface dose measurements, and calorimeter for high dose measurements. In radiation protection, personal dosimeters like thermoluminescent dosimeters (TLDs), optically stimulated luminescent dosimeters (OSLDs), and film badges help record cumulative exposure for healthcare workers and lab staff. These dosimeters ensure that those who work around radiation are not exceeding regulated exposure limits. Now, let's talk about uncertainties in dosimeter measurements, which are crucial for the reliability of these readings. Type A, or random uncertainties. These arise from random variation in measurements, like fluctuations in radiation source output or variation in dosimeter sensitivity. They can be statistically analyzed and reduced by taking multiple measurements and averaging them. And type P, or systematic uncertainties, result from consistent errors like those due to calibration issues or environmental factors. These uncertainties are predictable but not easily reduced. Total uncertainty in a dosimeter reading combines both type A and type B uncertainties. It is calculated by taking the square root of the sum of the squares of individual uncertainties, a method known as root sum of squares or RSS. Selecting the right dosimeter involves considering several key properties. 1. Linearity. Linearity is the dosimeter's ability to maintain a consistent relationship between dose and response. For example, if the dose doubles, the reading should also double. Energy dependency. Some dosimeters respond differently to various radiation energies. Ideally, a dosimeter should have minimal energy dependency, or it should be correctable if energy dependence is known. Dose rate dependency affects dosimeter response across different dose rates. Accurate dosimeters should respond uniformly regardless of dose rate or be calibrated accordingly. And finally, directional dependency. A dosimeter response can vary based on the angle of incident radiation. The best dosimeters are as directionally independent as possible to avoid errors from angle variations. To sum up, radiation dosimeters are essential tools in clinical and radiation protection settings. Understanding the types of uncertainties and key properties like linearity, energy dependency, dose rate dependency, and directional dependency ensures accurate measurements. And stay tuned because I'll be making more videos on clinical dosimeters and exploring how each type works in detail. Thanks for watching and see you next time.